Okay, this is lesson 4.1/4.2, and this is going to be an introduction to quadratic relations. Part 1 is just an investigation on nonlinear relations, so that means things that aren't lines. And we're going to build that into actually the second lesson, Introduction of Quadratics. So we're going to kind of do two at once. Now, this lesson is split up into 4 parts. It's a fairly sizable section of the unit. So you're going to get 2 days to work through it. I would suggest doing as much as you can on the first day, and then the second day finishing it off. If you split it up into 2 sections, 2 videos each day, should be good to go. The videos won't be super long. It's just I wanted to break it up into 4 natural topics. So the first topic is just an introduction to what a quadratic relation is. And we're going to start with some definitions and properties so that you have them, and then I'm going to show you what that actually looks like. So to start, the graph of a quadratic relation follows the equation y equals ax squared plus bx plus c. And the graph, when you graph it, the shape is called a parabola. It's spelled parabola, but it's pronounced parabola. And if you take a look at the equation that we're very familiar with, the y equals mx plus b, it lines up pretty good here with that term and that term. The mx looks like this bx term, and this b looks like that c term. It's just missing this first part, this ax squared, and that's actually what gives the graph of a quadratic relation its parabolic shape, because that term is called the quadratic term. It gives the graph its curve. And you're going to see more of what this quadratic looks like, but it's what makes it curve. And the reason why it ends up making it curved is because if you have negative and positive values of x that you plug into this equation, when you square something that's negative, you end up with a positive. When you square something that's positive, you end up with a positive. So no matter what value of x we plug into this equation, we're going to end up with a positive answer. And that's kind of what this graph shows. It shows that we're always pointing up. And we can have parabolas that go upside down. We're going to see more of that in the future. But it's this term that makes it different from a line. It's this term that makes it quadratic. This second term, this bx term, should be pretty familiar to you. It's the linear term. And it's the part that makes it a line. And the last term, c, is the constant term. Constant means we're not going up or down, we're just remaining the same. If you remember equation of a line, that b was the y-intercept. In fact, this c is also the y-intercept of our parabola. So there's a similarity there. I want to give you some terminology about parabolas, and then we're going to put them on a graph so you can see what it looks like. I'm going to scroll down here. The vertex of a parabola. We know vertexes as corners of shapes. It's the point on the graph with the greatest value of y if the graph opens down. And this point is known as the maximum. So that means if the graph looks like this, that would be our maximum vertex, because the graph doesn't go any higher than that point. The vertex of a parabola is the point on the graph with the smallest y value if the graph opens upwards, and that's called a minimum. So what's that mean? Well, that means if our parabola looks like this, that point at the bottom is called our vertex, and this vertex is a minimum because it's at the bottom of the graph. Now a parabola can only either open down like this, looking like an N, or open up, looking like a U. The word up has a U in it, and the word down has an N in it. So one way you can kind of remember, what the shape of a parabola is. If it opens down, it looks like an N. If it opens up, it looks like a U. Now, if it opens down, that point, vertex, the top, is called the maximum. If it opens up, the vertex is at the bottom, so it's called the minimum. That's all we're trying to say here. When the quadratic relation is used to model a situation, the point at which the parabola crosses the y-axis is called the initial value. Just like it was with lines. If the constant values, sorry, that's the a values, that's the number in front of the x squared of the quadratic, are positive, that's when we get our parabolas that open up. That's when we get our ones that look like this. And if the constant value, the a value at the very beginning of the quadratic is a negative, our parabola is going to open down. And that's how we get our two shapes. How can you remember this? Well, positive people generally smile, and people that are negative generally frown. There you go. Frown, down, positive. Doesn't rhyme with up, but looks like a smile. A parabola is symmetrical. That means if you split it in half with a line, both sides of the line will look the same. Symmetry. The line of symmetry is called the axis of symmetry. And the vertex will always be on the axis of symmetry. That point at the bottom, if it opens up, and at the top, if it opens down, will always be in the middle on that axis of symmetry. If the coordinates of the vertex are h and k, like for an x and y point, then the equation of the axis of symmetry will always be whatever the x of the vertex is. And if the parabola crosses the x-axis, the x values of these points are called the x-intercepts. I'll write it over here. So that's a lot of properties all at once. Let's put these on a graph so you can see what I'm talking about. Here's a picture of a parabola. We've got our Cartesian plane here. And we've got our symmetrical, it was supposed to be symmetrical. I don't know what happened with the drawing application, but let's pretend it's symmetrical. Parabola. And all of those features we just talked about in the last page, we're going to label them on the graph so you can see where they are. This point right here at the bottom, splitting in half, the minimum value, that's our vertex. And because our parabola opens up, that vertex is a minimum. So we'll put that here, minimum value. This parabola does not have a maximum value because our parabolas will continue forever in the upward direction. If our parabola opened the other way, we'd have a maximum value, but we would not have a minimum value because it would go down forever and ever and ever and ever and ever and ever. Where our parabola crosses the y-axis, that's our y-axis, this is our x-axis, that point right there is called the y-intercept. And where our graph crosses the x-axis are called the x-intercept. Notice our graph crosses the x-axis twice. And we're going to look more at this in later lessons, but a parabola can either cross the x-axis twice because the vertex is below and we're opening up, but if the vertex was here and we were opening up, it wouldn't cross it at all. And if the vertex was right on the x-axis, it would cross it one time. So there's actually 3 different ways a parabola can behave around the x-axis. And finally, the dotted line in the middle here, the line that's splitting our parabola in half is called the axis of symmetry. So now that we've labeled a parabola, we're going to try to pick off the values that represent these things with some examples. So we got a table here. There are 3 parabolas, and we're going to try to pick off all these features. I'm going to do 2 of them, and I'm going to save one for you to do. I'm going to save the middle one for you. So I'm going to do this one and this one. So let's take a look. Vertex. Vertex is that turning point where the graph goes from down to up, or in the case of this one, up to down, where the graph turns. So our vertex is right here, and the vertex is a point. So we need the coordinates for our vertex, and our vertex would be -1 for x and 4 for y. So -1, 4. Now our graph, since it has a vertex at the bottom of the graph, is going to have a minimum value. It's not going to ever go below -4. I don't know why I wrote +4. It's never going to go below -4. So the minimum value will be when y is -4. It's never, the y values are never going to go under -4 because that's the lowest point on our parabola. The axis of symmetry is the line that goes right through the middle of the graph, and it always crosses at the vertex. And if you remember how to write the equation of a vertical line, since it goes through the x-axis, we write x equals, and since it crosses the x-axis at -1, we write x equals -1. Now, if you take a look at this, these 3 things have something in common. The vertex is made up of the axis of symmetry for x and the max or min value for y. So if you look, x equals -1, that's the x of the vertex. Y equals -4, that's the y of the vertex. That vertex is really important because it shows the axis of symmetry and it shows the max or min value. Zeros. I'm going to relabel this. X-intercepts. Now the reason it was called zeros is because it's where the y value is 0 on the graph, and where the y value is 0 is where the x-intercepts are. So it's here and here. So the x-intercepts are points. We have 2 of them, so we need to write the coordinates of 2 points. Well, since the y value would be 0 at both of these are going to have y values of 0, and the x's are -3 and 1. So those are our x-intercepts. Direction of opening is the next one. Direction of opening just means, is this parabola opening up like a U or down like an N? Down like a frown, up like a smile. Our parabola is opening up like a smile, so we can say up. And the last point is our y-intercept. So let's go back and look at our graph. Where do we cross the y-axis? Well, we cross the y-axis right here. That's at -3 for y. If we remember, y-intercept's a point, so we would write 0 for x, -3 for y. All right. I said I was actually going to do 2 examples. I am going to leave both of the next 2 for you to try. I think that we did a pretty good job with our first example. The trickiest part of the next 2 is that sometimes they don't necessarily cross at nice points, so just try to approximate as best you can. Like the y-intercept of this one looks like it crosses at actual 0.5, and the x-intercepts look like they cross a little bit off, not exactly on there. So do your best to approximate those values, and then check your answers on the course website's completed solutions. And that's it for part 1. Thanks for watching, and I'll see you in part 2 where we look at the quadratic relations rule of 3.